Hello everyone. Today we're going to be going over a particular special case when we're talking about gravitational energy. In this one we're going to be talking about launching something really far forever, which is referring to something's escape velocity. The common idea about gravity is if you throw something up, it's going to come back down, but that's not always true because you could throw it really hard, really fast, and if you throw it fast enough, then you'll be able to break it free from Earth's gravitational pull. Now, this isn't actually particularly easy because Earth's gravitational pull extends infinitely outward. So to throw something, to get it infinitely far away from Earth, you probably need to throw it really fast. But we can actually find out exactly how fast you need to throw it to make that happen. So it should stand to reason here that if you want to free something from Earth's gravitational pull, you need to supply it with enough kinetic energy. Let's put that in there to match its change in potential energy from the surface to its potential energy at infinitely far away. Because if we consider our potential energy formula, remember E sub P is equal to negative G m over R. This is the gravitational potential energy. Remember, that doesn't mean anything unless we are talking about it in reference to something. And when something is infinitely far away, there's no gravitational potential energy. Or if we actually take a look, there is also no gravitational force, Gmm over R squared, when R is infinite, right? So when R is equal to infinity, both of these values begin approximating zero. And so we would escape Earth's gravitational pull if we can bring it to R's infinity away. And so this means we need to input an amount of kinetic energy that equals the change in potential energy from surface to infinitely far away, which is zero potential energy. Let me fix that there. And so we would just say like, oh, okay, so my kinetic energy has to equal energy potential final subtracted by energy potential initial. And the kinetic energy we know as 1/2 mv squared is going to equal the final potential energy. We want our object to end up infinitely far away. We know that when R is infinite, that the potential energy is zero, so that's easy. Minus energy potential initial, that's negative Gmm over R. Those two minuses turn that into a positive, and I can actually divide both terms here by m, divide that by m, divide this by m. So we find that escape velocity actually doesn't depend on the mass of the object that you're flinging. That's really convenient. And so if I were to continue on here, half of the velocity is equal to Gm over R, because those negatives cancel out. And I would just multiply both sides by 2 to cancel that out. And then I can take the square root, and it seems that the escape velocity we would be able to find for any given planet, for any given space, is 2 times the gravitational constant times the gravitational source over where you're throwing from in this source. Are you throwing it from the center, or are you throwing it from the surface? Or this would work, this Gm over R, this R works for anywhere. So we could try to throw something away from the International Space Station, and we would just use the R from the International Space Station between the International Space Station and the planet. So this is really convenient. This is a universal derivation for the escape velocity. I didn't include the escape velocity on your formula sheet because the point isn't to have a formula for escape velocity. The point is to make this connection about energy. If I can input an amount of kinetic energy which will equal the work done that would take me from surface to infinitely far away, that should be enough energy to get something thrown out of the gravitational field or out of the gravitational influence of any particular object. So that's the idea. Is if you're like, I need to just give it enough kinetic energy to overcome my work. And if you've got that idea, then you can find the escape velocity in any situation. So let's go ahead and try it. What is the escape velocity for Earth? How fast, while standing on the surface of the Earth, do you have to throw something for it to leave the Earth forever and never come back? Well, let's start with something. And let's start from our fundamental understanding. If I throw something fast enough, it will go. So I need to give it an amount of kinetic energy that's equal to my change in potential. 1/2 times the mass of the rock times how fast I'm throwing it squared is going to equal, remember our final kinetic energy is infinitely far away, so that's 0 minus the initial potential energy, so negative gm m over r. Those negatives cancel out into a big old plus. These masses cancel out, and we have v squared is equal to, I multiply the 2 up, 2gm over r, take the square root of both sides, and so the escape velocity on the planet Earth is 2 multiplied by 6.67 times 10 to the power of negative 11, multiplied by the mass of my gravitational source, which is the planet Earth, 5.98 times 10 to the 24, and we divide that whole thing by the radius, because we're throwing from the surface of the planet, so that'd be 6.38 times 10 to the 6. And bringing up our calculator, we would be able to do this calculation here. So this is 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the power of 24, and we are dividing that by 6.38 times 10 to the 6, and we want to take the square root of this whole thing. And it seems that if you want to throw something outside of the gravitational field, outside of Earth forever, you're going to have to throw it at approximately 11,200 meters per second. So kind of fast, just a little fast. Something along the range of like 40 times the speed of sound. Divide by 3. Yeah, just a little over 30 times the speed of sound. So kind of fast. But if we were to live on a smaller planet, or if we were on an asteroid or something where the gravitational forces are less at the surface, we can find that there will be situations where you might actually be able to sprint fast enough that you leave the object entirely. And so that's just a fun little question, is finding what's the escape velocity for any given sort of mass. Well, last little question here is, does the mass of the rock matter? Well, what do we see here is we see that the mass of the rock was this a mass rock, and it totally canceled out. The answer is no. No, the mass of the rock doesn't matter. This escape velocity is something that is entirely mass independent of the object that you're flinging. The only mass that's relevant is the mass of the gravitational source. That's it for our special case of gravity, is finding the escape velocity. All we have to do is consider our kinetic energy versus work, and that's all. That finishes up all of the details in our unit, so the only thing left to do is practice and maybe look at some different styles of problems. Have yourself a good day, everybody. See you later.